Hello there. Hello, hello. So today I'm going to challenge myself a bit here. And so there's this thing called 6502 assembly. Yes, of course, there's assembly language. I mean, you can learn assembly language for a modern processor. Like the modern processors for computers are typically x86 processors. There's also ARM processors, and those are mainly divided into two formats, which are pretty similar. The main difference is like the order's reversed, and so there's the AT&T format. And where's my and at? I don't have the. Oh, there it is. 7, I think. My keyboard doesn't have this stuff written on it. AT&T assembly format, I guess we'll look for. And the other one is, yeah, Intel format. So they just have a couple of different syntaxes. So you can see, like, I'll try to make this big. For example, this move command does what it sounds like. It's moving something, but okay, in AT&T syntax, it's move L. And the order of these objects is reversed. And also, you know, AT&T syntax has these $signs everywhere and these percentage signs. And so the Intel syntax looks a little cleaner, I think. So you can compile those for your computer. That's cool if you want to learn them. I mean, there's lots of tutorials on that. You can also write C code and then you can get the assembly output of the code for a lot of languages, but C is going to be like one of the more straightforward ones where you have, you know, here's your code and here's the assembly output. Lots of tutorials. What was I going to say? I was going to say something and I forget. So, but 6502, oh yeah. There's tutorials and then there's also the x86 instruction set. So the Wikipedia calls it the instruction listings. There's actually, yeah, you can go to the Intel website, I think will give us the thing in like a PDF form or something. I'm not suggesting that everyone do this or anything, but this is sort of just, if you get interested in sort of the lower level of stuff and how these things work. I'm just gonna go PDF here because it's weird to me that it says the x86 instruction set has been around for nearly 40 years. Well, and they have backward compatibility, but I mean things have changed. Like there's more stuff than there used to be. I think it's not what I'm looking for. I'm looking for. Okay, the downloadable PDFs of all blah blah blah. Reference manual volume 1, la-di-di la-di-da. Maybe it's this one? Let me bring this up here, hold on 1 second. Bring this up. Okay, it's just taking a moment to load. Because it's going to be a big file. So what is this? Combined volume set, 4-volume set. This is not what I'm doing today. I'm doing a different assembly language, but I just want to... So this is 5,000 pages. Yeah. Basically the manual for all of Intel's chips. I believe at the end, towards the end are some like sort of cheat sheets of the instruction set kind of thing. So like, here's an instruction summary in the appendix. What else do we have? Let's just get to the appendices way towards the end here. 5,000 pages. No wonder it took a while to load. There should be charts. Well, okay, maybe Wikipedia is going to give us, yeah, a better rundown here. So let's see here. So this is added with 80286. So these are kind of, I guess, the basic instructions. So we have like a and, logical and, call procedure. I think this is a system call, which can tell the system to do two different things. Because it's not all just a question of what the CPU can do. Like, yeah, there's other things, like allocating memory, for example. So we have a bunch of flags. Those are used for arithmetic and stuff, and various things. A carry flag, for example, is used in arithmetic. There should be like an overflow flag at some point. We got stuff to do with floating points, decrement by 1. So these are, low-level commands. Jump command, MOV. Hey, what's up, Indian Gamer? How's it going? We've got a logical OR, push onto a stack. So there's a stack. That's sort of a computer science thing that you should maybe learn at some point, like the stack and the heap. That's just very general. That's just how a computer works these days. But how information is stored, how memory is stored. So then this stuff was added later, I guess. So this is going to be a little more kind of complicated. And there's not that much of this, actually. Pop A. Pop all general purpose registers from stack. And so your CPU has registers. Those are sort of this... there's usually just a few of them, or I don't know, these modern chips might have like a dozen or something. Day's gone very good? Nice. What'd you do today? So, but the register is basically when your computer is actually adding numbers, it's going to do that on registers. Like those are the little pieces of data that are basically close. It's what the CPU actually works with. It doesn't go into RAM and change RAM directly. It has to load in data and work with it somehow on the physical chip, right? So there's going to be the register. That's going to be like the fastest piece of data that it works with, if that makes sense. There's other, like there's a bunch of caches and stuff. So let's just search for like CPU cache. There's a bunch of stuff. I don't really know this stuff because I've never needed to care. But got CPU, L1 cache, L2 cache, L3 cache. So basically, and then RAM, hard disk. So out here on the hard disk / SSD and the network card, getting data from here is going to be the slowest. Like it's order of magnitude slower, or it's probably at least one order of magnitude slower than getting it from RAM, I would guess. And so RAM is your main memory. Okay, so then there's this L3 cache, and I really don't know how this works, but I think that your L1 cache is probably going to be memory that the CPU can access the fastest, except for the registers, which that's the actual data that the CPU is working with, if that makes sense. So yeah, I just wanted to briefly talk about some of this low-level stuff and point people towards things if they want to learn more about certain things. So there's an instruction set. So this manual, that's 5,000 pages, is pretty overwhelming. The CPU architecture has a lot of complicated things going on, I think. Over the years, they've ended up doing a lot of optimizations, like, because I don't know a whole lot about it, so I'm not going to really comment too much more. I'm just curious if there's going to be some useful tables at some point. I've looked at probably past versions that had some nice, useful tables, but I'm not really seeing it here so much. So I wouldn't really learn directly from this. Just I think it's good to know that it's there. Like that's the ultimate source of information about the Intel chip. And then I'm sure AMD, they have their own stuff that is analogous. I never know how to pronounce that. analogous, I think. Yeah, but that's not what we're talking about today. We're going to do 6502 assembly. And that is, okay, 6502 was a processor. So the original Nintendo Entertainment System had a 6502 chip. The Apple II had a 6502 chip. So in that era, there's also something called, I think, the BBC Micro, which, if you were in Britain at the time, was famous. There might have been, like, I don't know, the Amiga, maybe? I'm really not sure. It was used on a lot of things. Maybe not the Amiga. Let's see, 6502 computers. I'm not sure how much stuff will come out. What computers use the 6502? Apple II, Commodore, the PET, Commodore 64, BBC Micro, Nintendo Entertainment System, the Atari 6200, also aka Atari VCS. So yeah, and then yeah, so lots of things use the 6502, like what, in the 80s, okay, quite a while ago. But this was a big, really important chip. I mean, they made maybe like more than 1 billion of them. How many 6502 chips are there? I'm not sure if it's going to tell us directly. I've seen stats before, but a ridiculous number were made. Very important chip in the history of computing. And so there are different versions of 6502. So let's look up 6502 assembly instruction set. Okay. So stuff like this. So maybe we get a cheat sheet or something. So it's going to look more complicated than it needs to be in the beginning. So some of these are what are called illegal opcodes. And the illegal opcodes, if you use those, the government knocks on your door and you get arrested. No. Joke. But the idea is that these might do something that works, but you shouldn't use them because there are various versions of the chip, and that functionality of what the illegal opcodes are doing may change, okay? Because they're saying, don't use this stuff. Now, there are 256 possible instructions. So basically, and if you think about it, to make programs, you don't need that many instruction sets, really, or instructions. You don't need 256. That's quite a lot, actually. So I think this is a little... that's an SVG file. Can I bring that up here? It wants to open it in Microsoft Edge. Gross. All right. I got it. I'm just going to make it bigger. So, if we're dealing with the legal operations, I believe those are the all of these sort of yellow ones. And so, for example, this is decrement, increment, okay? This, I think, is store in the accumulator. Okay, so they all stand for something. We've got ands. We've got some kind of bit. I think this zero's a bit or something. It's some kind of bit operation. This is, I believe this is compare Y, compare X. So we have on this chip architecture, we have an X and Y registers. Okay. So before I go any further, I do want to just talk about, like, why would somebody want to learn this stuff, right? Other than being a huge nerd. And the thing is that at some point you might want to understand how things happen at a very low level on your system. So, and with programming languages. So, like, what most people consider a low-level programming language would be, for example, the C programming language. And yeah, I mean, low level is sort of relative. So, like, older programmers sometimes will refer to C as a high level programming language, because for them, assembly language is low level and everything else is high level, essentially. So low level means close to the metal. So you have very explicit control over exactly what's happening. Now, if you take it to another extreme, like for example, web programming, and you're writing HTML and it's in the browser and all that, sometimes, I mean, that stuff is cool, but sometimes it feels like you're dealing with this black box, sort of. And you're programming up here, and there's all this stuff below that's happening, and it's very hard to, say, reason about that stuff and figure out what the heck you want to do with it. Let me bring up OBS here, just because I might do a horizontal recording here. Where's my OBS at? There you are. Once we get into this. Okay, so yeah, we're learning 6502, and I did talk briefly about the instruction set, the assembly instructions that you would have for your actual computer. That's different. That's at x86, and the 6502 is an older chip used for stuff like this, Apple II, also the original Nintendo Entertainment System, and a bunch of old stuff. So I talked about that in the beginning of the vertical stream, so you can find that on my channel if you want to have more context here. But I think this is a great chip, and it's great if we can have low-level control, and really, I would like, it's sort of an ideal, you usually don't get this, but I would like to write programs and actually understand everything that's happening. Also, one of the problems, maybe part of the reason that, say, Windows sometimes gives you the blue screen of death and this kind of stuff, crashes, you know, it's much more complicated. There's a lot of, what is it called, multitasking. So it's managing multiple threads, doing different processes. There's a kernel that decides like how all of that is sort of scheduled, like in what order it does different things. And that kind of makes it will definitely make things more complex, almost kind of like non-deterministic, not explicitly so, but I mean, if you were, it could in certain cases. So it just gets a lot more complicated. So I think it's sort of, as a programmer, eventually, at least for me, it's sort of medicine for the soul to focus on these much simpler things. And I say simpler because it is. I mean, these yellow ones are all of the instructions in the language. So learning this, I'm sorry, that's easier than learning Python or learning JavaScript or learning Java or learning C or C++. It's fundamentally simpler. Does that mean it's easier to read? No. It might not be easier to read. Okay. So I've studied this. I'm not going to go through all the things. I'm going to find cheat sheets as I go. I have a goal here, which is to create some kind of function that outputs all the possible permutations. So if I Google algorithm for even permutations, for example. I love this website, and they've got an algorithm. And it's not a beginner thing, but sort of intermediate level programming challenge. They talk about this algorithm, and the steps are here. If you want even permutations, and then I think odd will also be easy. They talk about that. So it's this one with added steps, or yeah. Now this algorithm I like, and it's good because unlike other algorithms, a lot of the other algorithms, if you want even or odd permutations, what they'll do is they'll go through all of the permutations, and then for each one they check if it's even or odd. And that process, not only are you creating extra permutations, so that's expensive, but also the checking process is also kind of expensive, so it's very inefficient. So that's why this website in particular I like. So it's kind of a good intermediate level challenge. Whatever your preferred programming language is, try to read this and implement this. And then you can go on LeetCode and let's see here, LeetCode. Da-dee-da. I have to sign in all this stuff. But they have an area that says problems, and then you can search. And if you search for permutations, is it going to make me log in? Now we got this stuff here. So you can search permutations here. And there's a whole bunch of stuff with permutations. So these are nice little challenges to sharpen your sword and improve your coding. This is also good for a resume. And some other things I wanted to mention here. So permutations are related to group theory. So I don't want to scare away would-be programmers too much, because you don't, in normal programming, you don't need this stuff. If you get kind of advanced in programming, sometimes there'll be a lot of linear algebra. If you go into like data science, big data science or whatever, or if you go into sort of advanced 3D graphics stuff, or 3D games, sort of, and you know, don't be afraid of it. You'll be able to manage it. But if you want to go into the difficult stuff, typically it's linear algebra stuff. And there's lots of playlists online for that, including Essence of Linear Algebra is Fantastic by 3 Blue, 1 Brown. But then group theory is... I've been programming for like 10 years, and I've never needed group theory in programming. And I've never directly heard from somebody who needed group theory. There are scientists who work on things where group theory helps and can help make more efficient algorithms in some cases. But group theory is about symmetry. So, for example, the Rubik's Cube is a good example. The dodecahedron, crystallizations of atoms and stuff. So there's chemistry applications. It's basically all about symmetry. And so you can... I don't know why they're showing knot theory here. That's related, but sort of not directly. LinkedIn, hooray. Yeah, I'm not going to go and explain what all of group theory is, but basically the permutation groups are sort of the big daddy groups, and all other groups are subgroups of the permutation groups. So that's why they're sort of important. And then being able to come up with even and odd permutations is something I definitely want to be able to do. I've implemented this algorithm. I think I did it in C. And, you know, it took me a few hours or whatever. Had some coffee and sat down. I didn't do it on stream, no. But I did it on my own one of these days. And then... So since I've done that in C, my challenge now for myself, I'm not sure I'm going to be able to do it today, is to try to implement that algorithm in 6502 assembly. Now, I've never really written something in 6502 assembly. I've done tutorials, but I've never... This is like my first personal project, if you will. It would be really cool to be able to write Nintendo games at some point with 6502 assembly. Okay, yeah, so this is slightly harder, so it's better to start with this, which is just making permutations. And then, so if you look 6502 assembly online, there's a bunch of things, you can do things. There's also this tutorial that comes up. Let's see, skilldrick.github.io was somewhere in here. Yeah, that's the second result here. And so that's a tutorial. There's a lot of tutorials out there. And then at some point, I made flashcards with, I think, all of these legal instructions. And then if you ever make an emulator, basically, like if you made a regular Nintendo emulator, you have to be able to handle these instructions. And then, so what you would do is you would first just worry about all the legal instructions, which are these yellow ones, and then later, if you want to, you can deal with illegal instructions. And that will allow it to run more games. Most games should run with the legal instruction set. Okay, so I'm gonna just dive into it a bit, and I'm using. I like this one. So they have this nice little. Wait, this is what I was just talking about. Yeah. So I don't know if you can see. There's 3 pixels that are colored here. So what they're doing, this LDA. I'm gonna make this bigger. Can we make it bigger? LDA is loading the accumulator a bit, I believe, and then send to accumulator, something like that. I need a cheat sheet for this. So 6502 instructions cheat sheet. Let's take a look at this one. Why is it fuzzy? Why are you fuzzy? Hey Wolf, how's it going? I don't want to click on these weird links. I don't trust. Do not trust. That's all we have here? There's got to be something better. Yeah, what I want is these sort of, the language, like, I'll show you. So I want the, oh, good night, Wolf. What I want is, for example, SEC, it shows me set carry, right? That kind of stuff helps you remember what the heck this stuff is about. Okay, so, all right. Let me move this over here. So LDA is load accumulator. And STA is, I believe, oh, it's store accumulator, not send to. Okay, so if I just do one of these, I hit assemble and run, it's going to make 1 pixel. And that is white. That's interesting. So if I change this number to, let's say, 6, assemble, run, it changed to like a dark blue. How about a 0? Can we do that? Assemble, run. No. So this is, I think this is a address in memory. It says store accumulator. So there's probably an area of memory where it has this graphical information. So let's, yeah, we can control Z, get this back, run. And I believe this is trying to help us know where some of the information is. You can't see that. Hold on. But I don't know exactly. Yeah. So we know how to... One of the tricky things is going to be outputting information, right? So is there a way to print out to this console, maybe? Registers and flags, instructions, branching, addressing modes. I don't know if there's going to be an easy way to print out to the console. So it's reading the input, okay. Updating the game state. Rendering the game. Well, I think we'll figure it out. We'll figure out a way to output information. Let's just try to add a couple of numbers. How about that? So load X register. I want to put a number in the X register, I think. Let's see how to add 2 numbers, huh? It's not really a lot of A lot of commands, really. Store to, I think it's this STX, store to the X register. So probably gonna get the syntax wrong in the beginning. So I want to do something like this: store the number 4. But maybe I need this pound sign, dollar sign, maybe. Maybe the dollar sign might be for hex values. So any numbers prefixed with dollar sign are in hexadecimal. Okay. Anything with a pound sign is a literal number value. Any other number refers to a memory location. LDA pound $01 loads the hex value da-dee-dee, da-dee-da. So I'm guessing if we didn't have this pound sign, this means that it's a memory location, yeah. That's cool. We can step through the instructions one at a time, it sounds like. So we have A, X, and Y registers. Each register holds a single byte. SP is the stack pointer. We'll get to that later. Da-dee-da. This register is decremented each time a byte is pushed onto a stack and incremented when it's popped off the stack. Got a program counter. That's how it knows where the program currently is. We've got a bunch of flags. Okay, now they're commenting things. Okay, we can comment like that. So load the hex value C0 into the A register. So C, so the if this were an A, it would be 160. Is that right? I think. So I'm guessing, I think this number is 192, maybe. Anyway, so tax, transfer to the A, transfer what's in the A register to X. So here we're adding numbers already, so increment the value in the X register. So I wonder, could we have just stored things in the X register to start with? They loaded it in A and then they sent it to X. Add the hex value C4 to the A register. Anyway, so it sounds like it's just adding 2 numbers. That's cool. So I want to go in the direction towards this permutation stuff. This is going to be hard. Find the largest array index. So I'm not going to know how to make functions in the beginning. So let's assume, for example, well, let's kind of hard code some of the what would normally be the input variables. For example, let's start with making all the possible permutations of 3 items. So, the input to this algorithm is an array of length n, which is initially sorted in non-decreasing order. And its output is a Boolean value indicating whether A has been modified to contain the next permutation. So this lexicographically is, I believe, just the order. Like for example, just order. So like B is greater than A, 7 is greater than 6, and so on. Or there are no more permutations, A has been returned to its original non-decreasing order. So I've done this before, but I don't remember all the details right offhand. Okay, but I'm gonna bring up Krita. Hold on, so I can start drawing some stuff. 1 second. Okay. So, the first thing that it does, so it receives as input sorted in non-decreasing order, okay, which it generally is increasing order, but they might all be the same thing. That's why they say non-decreasing. So generally it's in increasing order. So suppose it's like 5 items and it's just ordered 1, 2, 3, 4, 5. Right? That makes sense as an example. So the first step that it's going to do is it's going to find the largest array index I such that the thing is less than I plus 1. So in our example of 1, let's just do 4, up to 4 for now. So it will first find this one. Why is that? The largest array index I such that this is bigger than this. So a plus 1 here, sorry. So when I is 3, it's here. Let's make these numbers different from the index values just to make things a little more clear. So let's say our numbers are 4, let's make them 6, 7, 8, 9. This is our input, 6, 7, 8, 9. So this is I equals 1, I'm going to say. I mean, whether we call it 0 or 1. Okay, let's call it 0. This is 0, 1, 2, 3. So when I is 2, which is here, it's going to look at 2 plus 1 is I is 3. It's going to look at the next value and compare them. That's this part. So it compares the A of I is the value here. I is the index. So it's going to compare, in this example, 0, 1, 2. It's going to ask the question, is this true or false? So is 8 less than 9? Yes. 8 is less than 9. True. Once it tries to go here, there's no higher value, so it's not going to work. Now we're going to worry about this later if no such index exists, blah 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 la-di-di-la-di-da, because that happens at the end of the algorithm. Actually, all of this happens at the end, so we're not going to worry too much about that yet. First, the important thing is that it's found this value, the second to last one. Then it goes, find the largest array index j such that a of I is less than a of j. Okay. The largest array index j. So it's looking for the rightmost number that is greater than this 8 here. Okay? That's what that's saying. Because the largest array index means the number that's furthest to the right. Largest array index. Such that the output value here, this value is greater. And we know it exists because in the previous step we found exactly such a pair here. That's what it's saying there. Since I plus 1 is such an index, j can always be found and is always greater than I. Okay. So in this example here, it's the largest array index j for which this is true is going to be right here, where j is 3, 3, because it's 0, 1, 2, 3. Okay, so we're almost towards the end of the algorithm here. So it's I think this looks daunting. That's why I said it's a good challenge for people who aren't beginners. But you work through it one step at a time. And for me, the first day that I found this, I was in the middle of working on something already, and I looked at this and tried to understand it. I didn't really understand it at first, so it took some time. But the next day, sat down with some coffee, started my day, and worked on it, and got through it. But it's not the easiest stuff to read this kind of text. So, and then we're going to swap these two, the values. So we swap them, so it becomes 6, 7, 9, 8. This swapping action is also called a transposition. Just useful information. So we swap them, and now it's going to reverse the order of the elements from a to I plus 1 to the end of the array. A to the I plus 1 was this last thing in our example. So it's going to reverse the order here, but reversing the order of one element leaves it unchanged. So it's going to do nothing. And then it's going to return true. Return true. So you notice what we did is we sort of went to the end and we just swapped these last two items. So we should kind of remember that when this algorithm starts, it is going to receive stuff in increasing order or non-decreasing order. And so because it's in that order, it's basically going to go to the last two elements and it's going to swap them. Unless, I don't know, I don't actually know what happens. I haven't really thought about what happens when it receives input where numbers are the same, because these are not less than or equal to. So it's going to be different. Things are going to be different if it received 6, 7, 8, 9, 9, 9, 9, 9 as input, for example. But I haven't really bothered thinking about that too much, because for my purposes, I don't really care. I'm not gonna have repeat elements in what I'm doing. And it's a little simpler to not think about that. Hooray. Yeah, so we return true. So let's think a little bit about the return values. So it says its output is a Boolean value indicating whether A has been modified to contain the next permutation. Then it will be true, which we're doing true. Or there are no more permutations. So at the end of this algorithm, it does this process, and so actually it stops here. It's not going to swap anything. It's going to stop here. If no such index exists, then we found, well, we'll deal with that when it comes to it. We'll make sense of it then. And it returns false, and then this loop should stop at that point. So I think we should read this part as well. So to enumerate all permutations of an array A, we simply sort it in non-decreasing order. So when I say this, I have to translate to my head increasing. We sort it in increasing order. That's the initial input to the algorithm, okay? And then we run that algorithm repeatedly until it returns false. At which point we're done. So what is this? Initial sorting of the array is not necessary if we store a copy of it somewhere else and run the algorithm repeatedly until A returns to its original state. Okay. So yeah, I think I've actually explained all of how this works, but I think it's probably overwhelming for any normal human. And also I haven't really demonstrated that this actually works. But that's going to be homework. If you want to reason in your head how this is going to continue. Like for the next iteration, I'll just show maybe 1 or 2 more iterations here. Let's see. So we've outputted the second permutation, 6, 7, 9, 8. And now, so it returned true, and we're going back through another iteration of the loop. So we're going to find the largest array index such that this conditional is true. What that means is it's now going to go to here. This a of I is right here. So I is equal to 1. Because for this point, it checks is, so when I is 2, it checks is a of I, which is 9, is that less than 8? No, it's not. So this is the next value. Then again, kind of skip this because that only happens at the end. That happens if no such index exists. So don't worry about all this until then. This is actually the hardest sentence in all of this to understand anyway. So it's nice we get to skip it. So then it says find the largest array index j such that this thing is true. So we already have this one. So we just have to check is 7 less than 8. Yes, it is. 7 is also less than 8. So what it's going to do now is it's going to swap 7 and 8. 8, 9, 7. Yeah. And then it's going to reverse the order of the elements of a plus 1. So that's starting here. So it's going to reverse them. So it hasn't outputted this yet. Seven, 9. This is the next output, and it returns false, and then the loop continues. All right, so I'm not going to demonstrate that this works. I went on a few walks over a couple days and worked it out in my brain and sort of demonstrated to myself that this is indeed going to generate all the permutations. Yeah. It's a little complicated, you know? But that's how the algorithm works. That's how it works. So I've implemented this in C once before. Now my task, my project is to do this in 6502 assembly. Hooray. So what's the first thing? We need this data, and then we need to be changing. We need to be, checking. We need to be comparing each of these. So let's try to do a compare in assembly here. This was adding numbers, I believe. We're doing incrementing. It increments and then it adds numbers. Let's get back to some comparison stuff. Here's branching, which is going to have compare. So this is compare x here. So far we've written basic programs without any branching logic, la-di-di, la-di-da, certain flags. Looking at B and E, branch on not equal, so that's the next thing here. So this text is explaining what's happening here. So first we load the value of 8 into the X register. The next line is a label. So these are, I believe these are like functions, basically. Or they're, you know, the analog of functions in assembly. Labels just mark certain points in a program so we can return to them later. After the label, we decrement X. So it's going to be 7. We store it in this spot in memory, which corresponds with the top left pixel. So I wonder if I cut this out, assemble, run, we get this yellow pixel up there. So it'd be nice to have a little thing that, oh, we have notes here. Oh, okay, yeah. So notes. Cool, we have a random byte generator, that's nice. We have the ASCII code of the last key pressed. Okay, that's for input. Memory locations of these map to the screen pixels. So that's, yeah, 200. That's the first screen pixel. So if we did 5FF, should be the last one. Assemble run. Yeah, we get the last pixel here. Coolness. These notes again. Different values will draw different color pixels. And then it has the map of these pixels. So that's why 0 didn't show anything, because it's black and it's on a black background. So we have all these colors. 16 colors, looks like. Including black and white. Coolness. Alright, so assemble run. Let's see what's going on. So we've decremented, we've stored into the top left pixel in memory here, compared to the value of 3. So we've stored, STX stands for, where's STX? Store X register. So it's storing the X register. So we load into X, the X register, the number 8. We decrement it, so it's going to be the number 7. We store whatever's in the X register into this spot in memory, which corresponds to the first pixel. And right now it's the number 7. So 7 is yellow. So run. Reset, maybe? Reset, run. I don't. This might be a bug that's not letting me assemble this again. Maybe if I refresh the browser here. Assemble, run. It's not coming out yellow. Oh, well, there's more stuff going on. So if I get rid of that, assemble, run, now it's yellow. Okay. Okay, coolness. Okay, then it says, then compared to the value 3. So that's this one. So we've got the number 7 in this position in memory. We compare it to the number 3. So CPX compares the value in the X register with another value. If the two values are equal, the Z flag... Hold on, I need more coffee. Where's my coffee? No, I think I'm out of coffee. I'll drink milk. If the two values are equal, the Z flag is set to 1. Otherwise, it is set to 0. So Z flag being on, or set to 1, means that they were equal. So it's saying, like, yes, they were equal. The next line, BNE decrement, will shift execution to the decrement label if the Z flag is set to 0, meaning the two comparisons were not equal. Okay, so what does this do? So it's going to decrement. How does it know what to decrement? Let's see. Oh, the decrement label. This is the decrement label. This is not an instruction, it's a label, right? So it's looping. So if these are not equal, it will go back here, it'll decrement. So then it goes to 6, and it's going to loop around until it becomes 3. And then 3 will set the Z flag to 1. And when it gets here, it should continue forward, storing whatever is in X in the next position in memory. So this makes sense to me now. So 3 is cyan. And, 4 B and E will... So branch if not equal, I think, is the thing. Will shift execution if they're not equal. Yeah, branch if not equal. This is cool. We've got a loop, decrementing, all kinds of stuff going on. Good. So I get that little program. That's nice. In assembly language, you usually use labels with branch instructions. When assembled, though... So a little interesting note. This 6502 does not have division as one of the instructions. Division in assembly language is a little complicated. It's too complicated for the 6502. So if you want division, you're going to have to implement your own division function. That's how low level we are here. When assembled, what is this about? Okay, branch instructions can only go forward or back around 256 bytes. So only used to move around local code. For moving further, you'll need jumping instructions. Okay. And I've seen jump. There should be JMP in here. Where's JMP? I feel like there should be there, but whatever. Yeah, there's something about addressing modes I don't really know about. Maybe... I think this information we maybe don't need for our purposes today. The stack, I don't... Are we gonna need the stack? We might need the stack eventually here. It's like any other stack. The values are pushed onto it and popped off it. So it's between these values. Stack pointer is initially FF, which points to memory location. Okay. So it's kind of starts off pointing sort of at the end of the stack, in a sense. Well, it's the beginning, but it works, just goes up or down, depending on what you think, how you think of it. When a byte is pushed onto the stack pointer becomes FE, and so on. Two of the stack instructions are, okay, push accumulator, pull accumulator. Oh gosh, so I want to start working with the stack a little bit. So let's bring this up in another window and start with the one that had branching. This one, let's start with this. PHA and PLA. So X holds the pixel color, Y holds the position. So we start at 0 for both of them. The first loop draws the current color as a pixel via the A register. So what was TXA again? TXA, transfer X to A. So it's going to transfer it's going to transfer 0 to A in the beginning. Then the STA was, I was thinking of it as send to, but it's not. Well, it kind of works the same way. Store. So I'm not... is this an offset, I think, maybe? I'm guessing this is an offset, so it's going to be sort of this plus this. So we're sending the value of 0 to the accumulator, to the A register. Then we are storing that value that's in the A register to the spot in memory, which is the first pixel here. Then we are, is that pulling or pushing? That's a push. Push the accumulator. So we haven't, up until here, we haven't stored anything on the stack. So I think, so we're pushing onto the stack here with this. Now we're going to increment both x and y. We're comparing y against the number 16. So let's read more of this. Draws the current color as a pixel. So this is probably, this is 16 pixels because we had 16 numbers. So probably once this is, once y is at 16, then we're going to exit this loop. That's the idea. So branch if not equal, so it's going to come back to iterate through the loop. Yeah, loop until y is the number 16. Right, so it's going to push it to the next value in the stat, or yeah, I get it. So it's not only putting these values out as pixels, but it's also pushing this information into the stack. I see, but the 16 values this is actually 32 values. You can see it starts repeating and going back down. So that's what the second loop is going to be about. Second loop. So now we're pulling. So when we exit here, y is 16 and x is 16. And yeah, so we're pulling from the stack. Where does the value go? I guess when you pull from the stack, it just, the data just disappears. We don't need it anymore. Yeah. So we're sort of popping, right? Popped or pulled, yeah. Pop it off the stack. So this gray value actually is being removed from the stack first, but it's still in the X register. Now, store the accumulator with the Y offset. Because when Y got to 16, it was never stored in memory. We haven't stored it in memory, so now we're storing it in memory. So actually, is that going to be the first gray value? I think this is the first gray value. Then we increment y. Okay, so now y is 17. CPY, compare y, okay, with the number 32. And branch if not equal, so it's going back. So now we're here. So we're not even dealing with x anymore. Now we're just dealing with the stack. We forget about x. It's irrelevant now. So that gray value, let me think here. Oh, I see. So when we did this, I said it was popped off and it disappears. That's wrong. It's popped off and it's stored in the A register. That makes more sense. So it was in the A register. The value of probably 16, right? On the last let's talk about the last iteration of this loop. And the last iteration of this loop, well, first, so x and y, let's talk about when they get incremented to 15. This compares 15 against 16. They're unequal, branch if not equal, so we come back here. So x and y are still 15. TXA was transfer x to a. So it's going to transfer 15 to a. So number 15 is being... Okay, but it's 0... It's... The colors are 0 through 15, huh? Okay. So the number 16 actually doesn't correspond to a color. 15 is the last color, because it's 0 through 15. 0 through F, essentially. Let's check the notes here. 0 through F, yeah, is the light gray. Okay, so we're going through here. We're going through here the last iteration. X and Y are 15. We transfer the X value, which is 15, to the A register. So the A register has number 15. STA is send to accumulator. STA is store accumulator, excuse me. Store accumulator in this thing. So the number 15 is going to be stored here. Number 15 corresponds to light gray. So this is where the first, okay, the first gray, light gray pixel is being created now. Then we push A to the stack. So we're now pushing 15, the number 15, for the first time to the stack. We increment x and y, they become 16. We compare this, it becomes true, and we exit the loop. So now x and y are 16. We enter this loop. Need more drink. So x and y are 16. The PLA is going to be pull. So it's popping off the stack. And what's the last number on the stack? It was 15. The last number on the stack is 15. Yep. So we're taking the number 15, removing it from the stack, putting it in the A register. Now we're going to store what's in the A register again here. So this is the second light gray pixel. Then we increment y. So y now is 17. Compare, and it's going to continue with the loop. Y is 17. And then this is going to loop until y gets to 32. Let's talk about the last iteration. So let's say we're looping through until y gets to 31. So y is 31, compares here. It's not equal, so we go through the loop again. Y is 31. And what's the last thing on the stack at this point? I honestly don't know. But it's the last thing that gets put down here. Because when we started here, y was 16. And now it's 31. Because if we counted, if 16 through 32 all created pixels, that's actually 17 pixels. If the number 16 and the number 17 created pixels, that's 2 pixels. Even though 17 minus 16 is 1, because we're counting both 16 and 17, it's 2 pixels. So that's why I know. So 31, 16 through 31 will be 16 pixels. So when y is 31, we are creating with these two steps, we're creating the final pixel here. And that final pixel is going to be black. Then we increment y, and we exit the loop. Yeah, I get it. Hooray. Okay, I need an energy drink. Because we're going to implement this. We're going to try to do permutations with this crap. Alright, this is hard work, but I understand this code. Good. What are we going to do? So I think we want this kind of information to be stored on the stack. So to begin with, we're going to hard code the input. So let's say, for example, we load in the X register the number 4. That means that we're coming up with the permutations of 4 items. Okay, that's our input for now. We're just hard coding. So I don't know how to do anything else. Ooh, this is gonna suck. This is gonna suck, but it kind of be nice also. So I want to, based on this input, I want to populate the stack with the numbers that we want. So I'm just going to call this loop for now. Does this do anything? It makes stuff. I'm just going to call that loop for right now. So this loop is sort of decrementing. That works. We're decrementing x. And we're going to compare it with 0. Let's try to have this y thing going on. This is fun already. So okay, 2 spaces. LDY. The same thing. Let's make this the number 0. And I'm not sure if the order here is good, but I want to increment y. It's just inc. Is it inc y? I think it's INY or something. Where my increment at? Inc memory. Somewhere in here we have increment. It's INX or INY. That's how it's going to be. So INY. Syntax error. It doesn't like this. What did it do? What did it do in the other example here? I'm getting confused because there's so many windows up here. I see. STA will be okay. But we haven't loaded anything into A. So actually, I think so. I want to send from the X register to the A register. So it's is it T? I think it's gonna be T tax or TXA rather. TXA will send from X to to A. So let's just see. Can I comment this? I need semicolons, huh? So what happened here? So we have the number 4, which corresponds with cyan, I think. Number 4 is purple. Number 3 is cyan. Yeah, because we're getting decremented. So number 4, then we decrement it. We send the number 3 now to A, and then we take A and we store it in memory based on this Y offset. So what if we change the Y offset? Is that going to work the way I think? I see, yeah. Okay. So it doesn't change the value that we're storing. It changes this. It increments or offsets that. Let's start with x at 0 and just increment up. I'm not sure we need y. Okay, x is 0. And let's increment x. So x will start at 1. But okay. Let's use, okay, this is confusing, but let's use y as our input to the program. So y is our input to the program, and we're going to say 4 at first. Okay. Okay. And later we'll compare x and y and see, that will be our condition for the loop. So right now we increment x, so it becomes 1. We store it in this thing, or transfer or whatever. And then I want to store the accumulator. What was the memory address again? 200. Let me make this a little more sensible. So I want to go like this. Okay, these are sort of jagged, so I can choose them easily. All right. So it's 200, like that. $200. Okay, so it has y increment. First number is white, huh? Yeah. So far, so good. This is sort of pointless, though. I can see how it gets complicated because you only have the 3 registers, right? So if you want to store data, I mean, you could store it on the stack. You have a lot of choices, I guess, but anyway, let's just keep this increment. I don't care too much about the positioning of things right now. We can worry about that later. So we're simply making a pixel. We're outputting the pixel 1 essentially. So next we want to output the pixel 2. But we want to be iterating through our loop. So we need some kind of compare. So, but I think CPX, I think it compares with whatever's in the A register. CPX. So these are grouped. We've got transfer, miscellaneous. We've got calculate. And the CP stuff is here, so it says bits, whatever. So it just says compare X and compare Y, but okay, to this thing. Okay. So we want to our sort of our iterator here is actually the X number. So we want to compare X, CPX, to whatever. Can I can't just use Y, can I? So let's just transfer whatever's in Y to A. And then, wait, so how do I compare, if they're both variables, how do I compare them? Let's just Google compare two variables 6502. Ooh. Are we just gonna hard code that for now? That's kind of sloppy. So I guess we should compare something against 0. So I think I'm going to use Y as an iterator and then compare against 0 and decrement. That will work. So we're going to be comparing Y against 0. So let's just output these in the wrong order first, because I can see it's easier. It's going to be easier to output this like 4, 3, 2, 1 compared to 1, 2, 3, 4. Eventually, we want 1, 2, 3, 4 for the algorithm, but that seems harder. Okay, back to their drawing board a bit here. Completely start over. 1, 2. We have the number. We're not even using X yet. Should we change this back to X being the thing? So X is 4. So we can begin. It was this command. I forget what it stands for. And this. We are going to use some kind of Y, but let's just LDY. Oops. The number 0. In A, we don't have. I think I can do this. I think. Let's see if that works. No, doesn't like that. So we want to send X to A. X to A. Okay. Purple is number 4, yeah. Now we'll decrement X. How does it work? What does it look like? Dex. So, okay, Dex. Decrementing X. And we want to compare CPX, compare against 0, branch on not equal. We're starting to get the hang of this. This is great. So we don't have a y offset, so it finished with the number 1. So we want that y offset, so we'll just do, I think we can do this, increment the y value. Hooray! So this corresponds to 4, 3, 2, 1. Nice. 4, 3, 2, 1, yeah, 2 is red. Just we want it the other way, actually. We want it to be 1, 2, 3, 4 instead. So we could just put this on the stack, and then, yeah, so we put 4, 3, 2, 1 on the stack, and then we just start popping off the stack instead. It's a bit of work. It's a bit exhausting. I might need a break. I gotta use the restroom. I'll be right back. I'm gonna make me some coffee here. So this is the first time I feel like I'm really writing assembly. I've studied assembly a few times over the years, mainly just because I wanted to understand how it worked. Never really actually wrote anything in assembly, to be honest. Coffee. I love coffee. So yeah, this content doesn't do too well on YouTube. At least not the way I'm doing it. Also, I'm learning as I go, so that's another thing. People usually prefer it if you already know your stuff a bit. I do know some stuff, but not at the level that I am teaching or anything. This is already cool, though. Yes, a bit of a serious task that I'm trying to do here. With the permutations. Okay, so I want to push this stuff onto the stack and then pop it off. So instead of even outputting this, or like I should say setting the memory here, we'll just push it to the stack. So let's look over here. They're talking about pushing to stacks at some point. I don't think it was that far down. Maybe, yeah, the stack. Here we go. So that's push, that's pull. So we do put it in A like normal and just push. So let's see how this goes. So this is going to be later. I'm just going to leave this as a comment. We are going to, was it PHA? So this is going to output nothing now, but it did assemble successfully. Okay, and then can I just call it loop 2? Let's just do something, make sure that assembles. It's fine. So loop 2, now we want to pull from the stack. So what we've done, we put 4, 3, 2, 1 on the stack, right? Yep. So we'll do a PLA, pull from the stack. So the first number that's going to come into A here is going to be the number 1. So then we do something like this. Let's see here. Let's set y to 0 again here. And we just need to loop through this. I think we probably need to increment something. At this point, x will be 0. I'm just going to hard code the number, this number for now. There's probably a way to, something better to do, but I don't know it at this point. Don't need to have this in the thing. I don't need these comments so much anymore. But we're going to want to compare something. How do we recover this number 4? Don't we have just random memory we can use somewhere, right? Like how about the memory location 1? Let's just see what they say about memory from the beginning here. The code is assembled starting at memory location 600. So I'm guessing up until memory 200, I'm guessing I can just use that memory. There's this many bytes of memory available to the processor. So the memory locations are from 0 to FFFF. So this is about making things a little faster. I do not care about that at this point. 0-page stuff. Blah, 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 blah. And I think that, okay, this is kind of what I figured out. There's like an offset, basically. Why can't be used with STX, but can be used with LDA and STA? I don't care too much about what I'm reading here right now. I still feel like, although it hasn't explicitly said anything, I still feel like I could maybe use that other memory. It hasn't really said like, hey, you can use, wait, memory locations here contain these values. Is this for the... Let's walk through this code a bit. So we're putting the number 1 in X. then putting this number 5 in register A. Then we store the accumulator. We store A in the memory location 0, 1. Then we load into A the number 7. And we put that in memory location 2. Load into Y. This is going to be the number 11, or sorry, the number 10. And we can pop that into this memory location. Load into A, whatever the heck this is. Okay, so this is what they're talking about, this indexed indirect. So memory locations 1 and 2 contain the values 5 and 7, because that's what we did here. Think of this as adding them together. In this case, X is 1, because we loaded 1 into X and we haven't really touched it since then. So this simplifies. Okay, so it's just adding together these values basically. Oh, that's interesting. But then it takes the bytes at 1 and 2. Okay, this is confusing. This is very confusing. I don't get it. I don't care. I don't get it. But I did learn some things here. So I think, okay, I'm going to assume that what I think about memory is correct. Where was I actually coding? Here. So I believe we can just send this to 1, right? Doesn't have a problem with that. So what we're doing is we're taking this number 4 that I'm treating as the input to the program, putting it in the memory location at 1. So, because I want to recover it, I want to use it again. So, yeah, because we were decrementing X and all this stuff, so we kind of lost that value. So can I load into X whatever was in memory position 1? Hopefully that's going to work. Then we'll continue to decrement X. And do this. This will be our loop. I really don't know if this is going to work. Stack filled. Okay, so I was hoping that X would be 4 here, but let's I'm gonna get rid of this for a second, and then if I do, let's say, we'll transfer X to A, and then we'll store A in position 200. So yeah, this is the number 4 getting stored there like I thought. Let's comment this out. For some reason before I wasn't finding jump, but it's right here, JMP. Yeah. So we're taking we're popping the stack into A. The problem is that y here is probably 0. Well, we've been incrementing y, but then we're resetting it as the default here, or as 0. So, okay. So y should be 0. Happy with that, but let's increment y. Oh, we're going to loop 1. That's a huge problem. We want to go to loop 2. Stopped, program end. Let's see, we have output here. So it's outputting, it looks like it's outputting 1, 2, 3, 4. Is that what we wanted? Yeah. 1, 2, 3, 4. That's exactly what we wanted. So this is working as intended. Hooray! Don't need this anymore. Wow, I'm writing assembly. Exciting. And yeah, without comments, it looks very hard to understand. So now we want this to output all the possible permutations. So we've got these 4 colors, so all the possible orderings of these 4 colors. And then we want to make it so that it will do this for different inputs. Anyway, so we've got the first step of this algorithm starting at the beginning. And then what we want to do is get to here and swap it. I think this task might be a bit difficult for me to implement. Like I barely understand what's going on here. So I think the task that I chose for myself for the level that I'm at is a bit of a tall order. But I also think you get better with things while you sleep. So I think this has been about 2 hours here today, and I think that I'll probably copy paste this. You know what? I'll put it in the description of this video after I finish. And then I might just write it again, like say tomorrow, for example, maybe. Start with this again as a warm-up and try to get to the next step of the algorithm. For example, I mean just swapping 2 of these elements, making a function that swaps things, for instance. So I don't necessarily think this is a bad idea for a task, but I think that my first time writing assembly, you know, 2 hours is good, because you get past 2 hours and your brain stops making sense of things of it. So I think just waiting, having a night of sleep, and then trying again another day. Not waiting too long, but tomorrow is probably the best day to work on it again. I think this is really good for the first time. It was only 2 hours. And I did a lot of extra explanation, so I could have gotten it done a little faster, but 2 hours. I think that's good for today. So thank you, everyone.